Welcome to the lesson 4 quiz, and I'm just going to go ahead and start off. Number 1 asks us for the correct statements about shear stress in a steel beam. And the unit shear stress, FV, is equal to V over dt, and I believe that's correct. And that means that the shear stress is equal to your shear divided by your depth of your beam times the thickness of the flange. I said flange, I meant thickness of the web. You could even do T sub W. So I believe that's correct. The shear stress should be checked for all beams. You can make a case to say no. I would want to say, well, sure, why not select it, but you can say no. That typically the shear stress will not control for all beams. Shear stress will not control for long beams. It's pretty much a given. Moment's going to, from pretty much all beams, moment's going to control or deflection. But so that's a maybe, a possible no. Since it says all beams, I would shy away from that. I would go to so far to say no on that. All right, number 3, the shear stress should be checked for beams with a short span and a heavy load. I would say yes, because the shear stress with a short beam is going to be less moment and a heavy load close to one of the supporting. If you want to draw tell you what I'll do is I'll draw, say you have a 5-foot beam and you have a really high, like 10K. That means that if you want to do your moment diagram, which, shoot, I don't want to do this. Let's say this is 1 foot over here, and this is 4 foot. And that means you would get, and this is 5 foot, and let's just go ahead and figure it out, the reactions. So you have this, let's say this is point A. Let's say it's 7 moments. That was kind of nasty. Sum of your moments about point A equals 0. You would have, let's call this B actually. This makes more sense that way. About B equals 0, and this would be AY. This is BY. Or you could call it the reaction RA and RB, does not matter, whatever you want to do. So we would have AY times 5 foot plus 10, but that's a negative 10 because it would do a negative 10 kips times 4 foot. And what would that equal? Equals 0 because B would not give you anything. So you have negative 40. So 40 divided by 5 equals 8. So AY equals 8 kips. And that means BY is going to equal 2 kips. Some of the forces in the Y direction. And you can figure that out if you want to, or you can just realize that's what it is. So your shear diagram is going to, and remember we're talking about shear here, is going to look like, well, that's way too long. Let's make it representative here. Your shear is going to go up 8, go down 10, and over 2. So this is going to be 8 kips. Where your moment diagram is going to go up real quick and then come down. But I don't know, I guess this doesn't really work too well to show that. 8 times what? 1? 8 times 1 foot, 8 kips times 1 foot is 8 foot kips. And I guess if you multiplied everything by 10, so you'd have 80 foot kips, and you'd have 80 kips, which 80 kips and shear is a lot more, I would say, wow, this is going to be a problem. This may be a problem more than your moment of 80 foot kips. You can overcome that pretty easily. But something you want to pay attention. So that's why I would say number 3. That was kind of a long way around, and maybe I shouldn't do that long for going forward. But as you can see, that I would say number 3 is a definite yes, because it just is. All right. The shear, I think I explained that enough. The shear, number 4, the shear stress should be checked for beams with a large concentrated load near the support. I would say yes, it's kind of the same thing. It's kind of the same thing. It's near the support. Either it's near the support, or if it's short, you're going to have less moment, and therefore you're going to have more problems. So I'd say yes to 4. It's kind of the same theory. Actually, my drawing is probably more like theory 4 than theory 3, or answer 3. So I'd say yes to 4. Number 5, if the beam is adequate to resist flexural stress, shear stress is not critical. I would say incorrect. If the beam is adequate to resist flexural stress, it says the shear stress is not critical, and that's incorrect given 3 and 4. You can have short beams will have higher shear stress because that moment is very small, because you don't have, moment is force times distance. So I would say no to 5. So I would say 1, 3, and 4, and it just so happens that B is 1, 3, and 4. So for 1, I would answer B. The answer is B. All right, going on to number 2. In designing steel columns, the larger slenderness ratio is used because A, it results in a smaller allowable flexural stress, results in a larger buckling load, results in a smaller allowable axial stress, is based on larger value of radius of gyration. I'm never a big fan of these word problems because I always think they're worded weird, and sometimes you could justify one. I would say the best is C, results in a smaller allowable axial bending stress, or I'm just talking over myself. Results in a smaller allowable axial stress, and that's because it's going to buckle. And it results in a smaller allowable flexural. No, not really, because we're not talking about flexural. We're assuming it's completely perfect, and therefore it's going to be buckling. KL over R has to do with buckling. Results in a larger buckling load. I would say it results in a smaller buckling load, and then is based on a larger value of radius of gyration. The larger sin. And that's incorrect, because a smaller radius of gyration would give you a larger slenderness ratio. So that's D is definitely incorrect. And I always find a little bit of test taking help here is to cross off the ones you know are wrong. I definitely know D is wrong because it's the opposite. I definitely know B is wrong. And then results in a smaller allowable flexural, but we're talking more about axial. So you could say, well, you could possibly make an argument for A, but C is definitely a better answer, so I'd go with C. C for number 2. All right, moving on to number 3. What is the allowable axial load for a W8 by 40 column of ASTM A36 steel if... Sorry, I'm going to erase here. A36 steel, so let's go ahead and write what we have. All right, let's write down assumptions. So we need to find P is our allowable axial. We have a W8 by 40 column of A36 steel, so we know this, KSI. If KL equals 20 feet. So we know KL, but we don't know R. For a section, now it gives us the section. The section is Rx equals 3.53 inches, and Ry equals 2.04 inches. A equals 11.7 inches squared. Alright, so it's asking us for P. And we remember a few things about this. We want to know KL over R. And we also remember that, let's just go ahead and do that, KL over R, and then we're going to have to go to the what's it called? The tables. Alright. So we know a few things. We know KL. Let's just go ahead and do. We also know that your weak axis is always going to control, since it is weaker, and it's going to buckle about that. It gives us no further information saying it's braced or anything like that. So we're going to go ahead and assume that the weak axis is our control, so it's going to be KL over RY, and we say 20. Let's go ahead and change that to inches. And then RY is what? This is F. This is allowable yield stress. There we go. And then RY is 2.04 inches. All right, let's go ahead and figure out what that is. 20 times 12 divided by 2.04 is 117.6. That's unitless. And now we go to the tables. And it kind of depends what you feel the most comfortable with. But I'm just going to go to the column section and see what table I come to first and see if I can use that table. Alright, and I'm flipping through columns. No. Okay, I'm on table 336. This is allowable stress for compression members of 36 KSI, specified yield stress steel. That's what we got. 36 KSI, and it has KL over R's. So we just go and we find the KL over R that matches up with R. Our KL over R, which is 117.6. And we go down, and 117 is 10. Let's just do this. What color am I going? Let's go green. 117 is 10.71. And 118 is 10.57. And if we interpolate between those two, let's do that real quick. And I always like to think of it as rise over run, so let's call this rise and then have the 1 be run, because we want to multiply it by run. Let me see if that makes sense. Okay, so if we subtract this, 10.57 minus 18 minus 17 is 1. 10.57 minus 10.71 is negative 0.14. So for every 1 you go up, you're going to go up negative that. Alright, and we're going up 0.6, so let's multiply that by 0.6. And we get 0, and that's, we get negative 0.084. And you could probably just go ahead and say, well, it's closer to 118, or 118, say 10.57. But let's go ahead and interpolate, and let's do both. So you get that, and you want to subtract that from 117. So 10.71 minus 0.084, you get 10.626. Alright, so that's what it is interpolated. It fits in here somewhere, 10.626. And we're going to multiply that. And this gives us your allowable FA, and this is in KSI, equals 10.626. So if we have allowable stress, we need to, how do we need to get to what our P is? And remember, stress, your axial stress, you can do S or FC or whatever you want to say, equals P over A. So you plug that in, you plug in your A, and it ends up, you just say, just arrange it, equals times A. So we get 10.626 KSI times A, which is 11.7 inches squared. I'm just writing kips. Alright, 10.626 times 11.7 equals 124. P equals 124.3 kips. And we look, and A is 124. So let's go ahead and go with A. We could also have just said, well, let's just use, it's closer to 118. 117.6 is closer to 118. Let's just use that. 10.57 times 11.7 equals 123.6. It would be close enough. So you could have just done that without interpolating. All right, I've run out of time, so I will continue with number 4 when we get back. Thanks.